So our next speaker is one of our senior fellows, Nadia Krook, and Chris Murray.
All right. Good afternoon, everyone. My name is Nadia Krook, and I'm a fourth-year PhD student. And as Ara said, I'm co-advised between Dr. Russ Composto and Dr. Chris Murray. And my work is in Act 3, where I am designing polymer coatings that control the alignment of anisotropic or non-spherical nanoparticles. And this is work that I brought with me this past summer to France as a 2017 cohort that traveled to Grenoble, working with Patrice and Manuel. So working in Act 3, Act 3 seeks to arrange novel nanoparticles to maximize the use of the solar spectra to create self-assembled nanomaterials for energy generation. And so our team's goal is to create optical waveguide coatings by synthesizing nanoparticles with primarily optical properties. So our research in Act 3 aims to tune the separation and the alignment of such particles into the most efficient structures. So optical anisotropic or non-spherical nanoparticles, such as cadmium selenide in this case, can be assembled into different orientations, and in this way on a liquid-air interface to elucidate the effect of nanoparticle orientation on properties. However, when we want to start thinking about applying this to a surface for a tent, as is the aim for REACT, we want to start thinking about putting these into some sort of coating technology, which is where my work comes in. And at the interface of Russ and Chris's group, I work on polymer nanocomposites that integrate nanoscale particles into polymeric matrices. And the benefit of these materials is that the resulting properties will possess properties of each component. So we can have the properties from the particles incorporated into a flexible, thin film, such as a coating. So some examples of some properties that we can incorporate into a polymer film are mechanical properties. So we can improve the mechanical properties of polymers, where in this case, clay platelets have been introduced into polymeric matrices, and by increasing the loading of the clay or the clay content, we can enhance the mechanical properties compared to the neat polymer system. We can also impart optical properties onto polymers. So in this case, we're incorporating gold nanoparticles into polymeric matrices, and then by increasing the loading and also just the incorporation of these particles, we can impart optical properties into the films. So the properties of polymer nanocomposites depend not only on the incorporation of these particles into polymers, but also on how they are arranged within the film, so how they're organized and also how they're aligned. So my work is really focused on the alignment of particles and what effect that might have on the properties of the resulting material. So we believe that through this, a new class of polymer nanocomposites could be revealed that would have a unique set of properties. So the analogy I like to use is with drinking straws. So imagine embedding drinking straws parallel into the substrate. So in this case, nothing could pass through the film. However, if we could reorient those drinking straws so that they're vertical to the film, now water could pass through. So the analogy here is, can we tune the properties of the film by changing the orientation of the particles? So could we change the properties whether they're parallel or vertically oriented in the film? So that's the goal of my work, is to create polymer nanocomposites with either horizontally or vertically oriented anisotropic or non-spherical nanoparticles. So there's different ways in which we could think about doing this. We could apply external fields, or in the case of Hitachi Chemical Company, they developed heat dissipating sheets by vertically orienting graphite particles. And the way they did that was they took this structure B, where they incorporated graphite sheets into a thermoset resin, and it started off with the particles being parallel to the substrate, and then they sliced up this structure and reassembled it to obtain structure D, which we see here in the image. And what they exhibited was an enhancement of thermal conductivity tenfold, going from structure B to structure D. But as I explained of how they created these structures, it was very much a top-down approach, so slicing and reassembling of the film to create these vertically oriented platelets into the composite. So my work aims to establish control alignment of anisotropic particles through self-assembly. So creating these self-assembled polymer nanocomposites with either horizontally or vertically oriented non-spherical nanoparticles. So the way I am looking to do this is using block copolymers to facilitate a hierarchical structure. So block copolymers are characterized by covalently binding two dissimilar polymers that are driven to microphase separate, because now we have these two polymers that are attached together that don't want to be close to each other, but they can only go so far. So this is a typical phase diagram for a block copolymer, where here we're looking at the chi-n, which is the relative attraction between the two blocks. So as we increase chi-n, mixing is discouraged, so these two linear polymers do not like each other. And then on the x-axis, we are changing the relative fraction of those two dissimilar polymers. And since they don't like each other, we can create these hierarchical structures from spheres to cylinders, lamellae, and then the reverse, as well as gyroids. So if the geometry of the template of these block copolymers and the chemistry matches the particles we want to incorporate into them, they can serve as templates for nanoparticles. So my work in terms of aligning non-spherical nanoparticles, I am working with a lamellar forming block copolymer, so polystyrene block PMMA, or I'll refer to as PSB PMMA, and a nanoplate system. So just to introduce my system further, I'm working with this model nanoparticle system, and block copolymer system, and I want to achieve different modes of orientation of the domains. So I have established a parallel alignment of the domains. So here we're looking at a TEM image of the cross section of a block copolymer formed on a silicon substrate. And the PMMA domain wets the silicon substrate. It preferentially wets the substrate as opposed to the polystyrene. And we can create these lamellar features parallel to the surface. And then if I change the surface chemistry of the substrate, making them neutral to both the blocks, I can actually get vertical lamellae. So here we're looking at a top-down image of the same block copolymer in a thin film with the domains oriented perpendicular to the surface. So now I've created a template with both domains oriented parallel to the substrate and domains oriented perpendicular to the substrate to serve as a guide for alignment of nanoparticles. For the purpose of this talk, I'm going to focus on my work with the parallel system. So I have my block copolymer formed, and now I'm going to incorporate the platelets into one of the domains. So in working in Chris's group, the platelet system that I work with is a model nanoplate system that's gadolinium fluoride doped with ytterbium and erbium. And it's synthesized through rapid thermal decomposition. And the reason why this is modeled for our purposes is that it's rigid, monodisperse, and I can tune the size and shape if I wanted to, depending on the precursors I use. But I picked this particle in this library because of the platelet shape, and also the dimensions are quite compatible with my block copolymer. So the domain spacing of my block copolymer is about 18 nanometers, and I'm incorporating a particle with the longest dimension of about 35 nanometers, the shorter diagonal of about 22 nanometers, and a thickness of about 3 nanometers. So when we think about incorporating a particle into a domain, we don't want to disrupt the local chain conformation and have too much of an entropic penalty to incorporate these particles in the system. So 3 nanometer thickness is quite compatible with my domain spacing. So as synthesized, these have oleic acid on the surface. So in order to incorporate them into a polymer matrix, I've changed the surface chemistry of my particles through a ligand exchange to functionalize these particles with PEG, so polyethylene glycol. And this is an ideal system in that now I've designed a particle that actually has a favorable attraction to one of my blocks. So in an undercooled melt, PEG and PMMA have an enthalpically attractive interaction. So I can disperse these particles quite well in PMMA. So this is the dispersion of these platelets with PEG on their surfaces into a 20K PMMA matrix with increasing loading. And we can see here that these are quite well dispersed. And as I mentioned, the nanoparticle system now has a chemical specificity to one of my domains, so the PMMA domain in my block copolymer. And you can look at these TEM images, and again, these are top-down images, and say, they look pretty dispersed, but they also look like they're pretty parallel to the surface already. So in order to investigate this a little further, I'm working a lot with tomography, where we can look at the out-of-plane dispersion of these particles as well. So this is taking a tilt series on the TEM of these particles dispersed in homopolymer. And what we see is that there are randomly oriented within the film, that there is no directed alignment in these films. So in order to establish directed alignment of these particles, I've incorporated them into my block copolymer. And so here we're looking at cross sections of these images with increasing loading of the platelets. So from 5 weight percent, we see that the particles are segregating to this lighter stripe, the lighter domain, which is the PMMA. 10 weight percent, we see that effect as well. However, when we start to get to 20 weight percent, we see that there's areas of disorder where the particles start to be randomly oriented, and then we do see regions of lamellar formation. And then once we increase loading to 25 weight percent and then 30 weight percent, the particles are randomly oriented. Our hypothesis is that in order to minimize the chain frustration, the platelets will align with their smallest dimensions between the block copolymer. So we can, just as a schematic, kind of a 2D representation of block copolymer. As we incorporate these platelets, the local chain conformation around these particles start to be disrupted. And then once you add too many of essentially these walls between these chains, now we can no longer form the lamellae. So what I've really probed is a system that can align nanoparticles, but that we do have some sort of limit in terms of alignment until we go from disordered at a certain loading. So this is my work with the parallel alignment. I'm also working on vertical alignment of platelets in block copolymers. And once we establish directed alignment and control over the orientation and structure of these particles, we can start thinking about how we can incorporate functional particles into these systems for our aims in REACT. So with that, I'd like to acknowledge both of my groups, as well as my collaborators in the Riggleman group, of course my advisors in France who made it possible and were instrumental in the success of my time there and for collaborations going forward, as well as Sigma Center facilities for all my electron microscopy support and then funding as well. Thank you.
We have time for a few questions.
Hi.
To go back to your interpretation regarding the frustration of the, so I'm going to ask a geeky question, someone that did that. Adding all those platelets, because you go really far, could it be just that you're moving in the phase diagram because you're increasing the volume fraction of one of the two blocks artificially?
Yeah, certainly. And that's actually something we were actually this morning talking about probing, is actually going off of the lamellar region and incorporating the particles to see if we can shift back into the lamellar region.
Or maybe change the, adopt a cylindrical
Right,
sense.
right, yep.
That's smart.
Okay.
So you said you made your particles by rapid thermal decomposition. You want to just talk us through that?
So I have precursors of the rare earth elements. So, for example, it is gadolinium trifluoroacetic acid would be a precursor. And so I incorporate all the precursors into solution with ODE and oleic acid. And then it is a fast ramp rate to the reaction temperature of about 290 degrees. There's a vacuum portion of that, and then the reaction under nitrogen.
So you put everything in one vessel, heat it up fast,
Yep.
and then you're done.
Yep.
Wow.
After 7 hours.
Okay, 7 hours. They're beautiful particles for something that sounds straightforward.
Do you think it's really important to have them all aligned very parallel and in one plane to get the final properties that you want? Or there could be some misalignments?
I think there could be slight misalignment. I think experimentally that even in some of these images, let's see if I can go back here. There is some slight misalignment even within the domain. So that's something else I'd like to look at is the effective block polymer molecular weight to see how that might affect the alignment just within the domain. If there might not be more variation in terms of the angle within the domain spacing itself.
Do you have any sense of whether these morphologies are equilibrium, quote unquote? I'm fascinated by the fact that you go from ordered to disordered with the nanoparticle inclusion, but I presume that you don't order these samples from the disordered state, like at the low volume fractions, that you don't heat to high temperatures and then come back into the ordered state. Do we know that they're not just kinetically trapped, for example, that microphase separation didn't get arrested or something because of the high volume fraction of particles?
That is a good point. We've thought about going above ODT and then coming back down. So that is a good question.
Tell them how you make the film.
So I do thermally anneal the films. So I thermally anneal them for, what was that?
You spin coat.
I spin coat them. Yep. So I spin coat them. I have as cast. I've looked at the as cast samples, and those are they kind of look like the 25 weight % where everything is well dispersed. And then I thermally anneal them for several days.
But with the particles, the viscosity could be higher.
Right. It could be. Yeah. Things could be. I
And
mean,
the
changing the
Riggleman-
dynamics of the system.
And Riggleman group is doing simulations, right, with Rob?
Unfortunately,
Yeah.
unfortunately,
We will have that.
this
Yeah, we'd like to
week.
couple that with simulations.
But
We
it's
have
a
time
solvent
after.
casting, basically.
Yeah. So I am spin coating them as well.
Just stop here. Nadia will be here after the
Don't
symposium.
indulge the person who gave you food this morning.
Yeah.
Okay.